In this video, we're going to be talking about motion graphs and how we can use them to solve some problems. So the examples that I promised you in the previous video, which if you haven't watched, go ahead and do so to get a better idea of how the motion graphs look like in different situations. We're focusing on three different categories of graphs: on the distance time, speed time, and acceleration time. If you are on IB level, you might be discussing the velocity time graphs and displacement time graphs, or position time graphs as we also call them. So this slide is a great summary of the message I want to convey to you with today's video. So again, we're gonna see everything through examples, but in summary, we can say that on a distance time graph, the slope of it would give you the speed, okay, because the distance over time, which is the slope on this distance time graph, is equal to the speed. On the speed time graph, the slope will give you acceleration, because speed over time is acceleration. And then if you work backwards, okay, the area under the curve on an acceleration time graph is going to give you speed, because acceleration times time is going to give you speed. And the area under the curve on a speed time graph is going to give you distance, as speed times distance equals speed times time, equals distance. Okay, that's a great summary. You can add this in your notes, and I really think it will help you remembering these key concepts. Okay, let's see now the examples. Okay, example 1. We have a distance time graph. We want to describe the motion and find the average speed. So you may pause the video now, try it for yourself, and then come back and compare with my answer. Okay, so we look at this graph. First thing we identify is which variable do we have on the y-axis. We have distance, okay? The distance seems to be changing, which means the object is moving away from the starting point, okay? So it's definitely not a stationary scenario. The distance is changing, okay? Now, if we find the slope of this line, which we define in math as rise over run, okay, the rise happens to be this length, which is equal to distance, and the run is going to be this length, which happens to be time. So distance over time from our graph is equal to the slope. Now we also know from theory that the average speed is defined as distance traveled over time. So combining these two relationships, we can conclude that the slope is going to give you the average speed, and the slope in this graph is going to be 10 over 5 rise over run, and that's 2 meters per second. Quite easy, I hope. Next example, we have this speed time graph. Same question, describe the motion. How far has the object traveled in 20 seconds? Pause the video and try it for yourselves. Okay, so again, the first thing we identify is which variable do we have on the y-axis, and this is speed, so it's different than the one we had before, okay? And we see that the speed is not changing, okay? The speed is constant over time. So we have motion, the object is moving, it's not stationary, and it's moving at a constant speed. We have defined speed as distance over time, and if we want to find the distance from this one, if we solve this equation for distance, it's going to be speed times time, okay? Now, we happen to notice that the area on a speed time graph, which is going to be the area of this rectangular shape, is going to be, again, speed times time. So, as we identified on the first slide, on a speed time graph, the area under the curve is going to give you the distance. So if we proceed and we do the calculation, the distance is going to be 20 times 40, and that's going to be 800 meters. Now the next example, we have a slightly different curve. So pause the video and try it for yourselves. Now in this scenario, if we try to describe the motion, we can see that the speed is changing over time. When the speed is changing, by definition, we know that we're going to have acceleration, since we defined acceleration as the change in speed or velocity over time. Now, if we look at the slope in the speed time graph, the slope rise over run is going to be the rise, which in this case is equal to the speed over run, which is going to be time. But this happens to be also our definition for acceleration. So from these two relationships, we can easily conclude that the acceleration is going to be given by the slope. So the slope on this diagram is going to be 40 rise over run 20, and that's 2 meters per second. And that's the acceleration which we got from the slope. But there is more information hidden here. Speed we defined as distance over time, and distance is speed times time. So I've just simply solved this equation for distance. And as we discussed in the previous example, on a speed time graph, the area under the line is going to give you the distance. So the area, which is equal to distance, is going to be now an area of not a rectangular, but an area of a triangle, which is half base times height. So 1 over 2 times 20 times 40, and this gives us 400 meters. Okay, so two different shapes, the triangle and the rectangular here, but the area under the curve is always equal to the distance, and that's the safest option for you to calculate the distance. Always follow the area. Now another example, describe the motion, find the total distance, try it for yourselves, pause the video and come back. Now, in this case, we have three different sections. We have three different types of motion which we need to describe. If we look at the part A, okay, line A in this case, or the from 0 to 4 seconds, we can see that the speed is changing over time. So it is accelerating since we have change in speed. Then from 4 to 10 seconds, the speed is constant, therefore zero acceleration. And from 10 to 14, the speed is decreasing, so we still have acceleration, like a negative acceleration in this case, since the slope is also negative. Now, if we try to calculate the total distance, okay, as far as acceleration goes for A and C, you can easily calculate that from the slope. The only difference is that the slope on A is going to be positive and the slope on C is going to be negative. Now, area A is a triangle, so half times 4 times 8, and that's 16 meters. B is a rectangular, okay, so this is what we're trying to calculate now for B. That's what we did for A, and then next is C. So it's a rectangular. What's the distance between 4 and 10? That's 6 times height, 8, that's 48 meters. And C is another triangle with the same dimensions, 16 more meters. So the total distance is going to be equal to A plus B plus C. This is something you should not forget to do. Okay, so add the three different areas together and end up with 80 meters. Now, someone might argue, I can see one shape here, and this shape is a trapezium. If you know from geometry how to calculate the area of a trapezium, okay, it's the large base, so in this case 14 seconds, plus the small base, which is the length between 4 and 10, so 6 seconds, times the height, 8 divided by 2, and this would give you, no surprise, the same result. So choose one of the two methods. If you have the time, do both and double check that you get the same exact result. Last example, we have acceleration time graph, and we need to just describe the motion and see what information we can infer from that. So pause the video and try it for yourself. Now, we have defined acceleration as change in velocity over change in time. So apologies, I've made a small change. So when you will try to solve this, okay, yeah, please excuse my mistake. So don't follow this graph, okay, focus on this one, okay, with constant velocity. So we defined acceleration as change in velocity over change in time, and if we solve this equation for change in velocity, it's going to be acceleration times change in time. Now if we look at the graph, we have on the y-axis, as we said, the first thing we identify is acceleration and a constant acceleration. So acceleration is not changing. Now, the area of this graph is going to be y times x, okay, if we have a rectangular. So it's going to be 10 times 8. But these are the values for acceleration on the y-axis and time on the x-axis, okay? So the area on an acceleration time graph is going to give you the change in velocity, which happens to be 10 times 8, 80 meters per second squared. So in 10 seconds, the velocity has changed by 80 meters per second, has increased by 80 meters per second, okay? So again, I want to leave you with the summary slide, okay, which I really hope it can help you, and how we can move from a distance time to a speed time to an acceleration time graph, what information we get from each one. So basically it's the slope and the area under the curve. And first thing you do is identify what you have on the y-axis, and then you know what you can get from the slope of this graph and what you can get from the area of this graph. I hope this video has been helpful, especially if you couple it with the previous video where we introduced the motion graphs. Let me know in the comment section if you have any questions, and make sure you like the video and subscribe to the channel for more content. Thank you so much.